All right, in this video, let's summarize some of the major relationships and concepts for a mass spring oscillating system. So the first is that the dynamics of a mass spring, if I pull it out, the force is proportional to the displacement, negative kx, meaning if I displacement positive, my force is back negative. Okay. Now in a vertical system, where I have a mass hanging on a spring, at its equilibrium point, gravity is also acting in the same direction. And then at equilibrium, I know that Fs is equal to Fg. And if we call it down as positive, then our negative Fs, let me just say Fs minus Fg equals 0, so Fs equals mg. So that K is mg over x. Alright, so we can use that as a way of finding K for vertical oscillating equilibrium. Now, once I'm at equilibrium, it oscillates in the same manner about equilibrium, whether horizontal or vertical. Now, another useful way of looking at these systems is via energy. So I know for energy, the total energy of a mass spring oscillator is its kinetic energy plus its spring potential. Now, I don't think we're going to be doing in this series any vertical energy problems, including the gravitational potential. So I think the energy problems we'll use are for horizontal springs only. And in that case, a couple points are of interest. At x equals 0, at equilibrium, I have U spring is 0, therefore my total energy is 1/2 mv max squared. So v max occurs at x equals 0. And at x equal a, maximum displacement, Ke equals 0. Therefore, energy equals 1/2 Ka squared. So one thing we can say from energy is that 1/2 Ka squared has to equal 1/2 mv max squared. That's a true statement. So those are ways where we can apply energy to the spring oscillating system. The period, we found, depends upon K in the mass. So the period of oscillation for a mass spring system is 2 pi square root of the mass over the K value. And since period is the inverse of the frequency, and the frequency is the inverse of the period, if I inverse this, I get that the frequency is 1 over 2 pi times the square root of K over m. So there are two more formulas and expressions that are important for solving mass spring problems, the period and frequency relationships. And finally, we derived the other day some motion equations for the spring system as a function of time. So we saw that the position as a function of time is equal to the amplitude times the cosine of 2 pi times the frequency times t. And remember, f is 1 over t, so I can use 2 pi over t for 2 pi f, however you want to express it. We also saw that the speed, or the velocity as a function of time, is negative 2 pi f sine of 2 pi f over t. So essentially flipped and shifted, same phasing though, constant. And then finally the acceleration as a function of time is negative 2 pi f squared times the cosine of 2 pi f times t. So we have our motion as a function of time equations, our period equations, our energy relationships, and our dynamics. And that's really a summary of all the different relationships important to solving problems with the mass spring system, oscillating system.